Yan. So, magandang araw sa ating lahat. So, ngayon, nandito na tayo sa chapter 6 or Structures and Properties of Ceramics. Bago yan, magpapakilala muna ako. Ako nga pala si Aljon Biocampo. At ang aking mga kasama sa chapter na ito ay sina Miss Vanessa Bora at Mr. John Edward Megano. So, structures and properties of ceramics. So, sa structures of ceramics, dito explain namin yung arrangement ng mga chemical bonds sa pagitan ng mga atoms. Then, sa properties of ceramics, dito ipapaliwanag naman namin yung mga katangian ng isang ceramic materials. So, contents. So, sa contents, naglagay kami ng introduction to ceramics. Ceramic structures, so under nyan yung crystal structures, silicate ceramics, materials of importance such as carbon and carbon nanotubes, imperfections in ceramics, diffusion in ionic materials, at ceramic phase diagrams. Next, mechanical properties, so under nyan yung brittle fracture of ceramics, stress and strain behavior, mechanism of plastic deformation. So, yan yung contents ng report namin. So, what is ceramic? Ceramics comes from the Greek word keramikos, which means burn stop. So, ibig sabihin, ma-achieve mo lang yung ganitong uri ng material sa pamamagitan ng mataas na temperatura or heat treatment process. Next, most ceramics are compounds, either ionic compounds or covalent compounds. So, sa ionic compounds, na bubuo siya sa pamamagitan ng ionic bonding. So, yung elements na involved ay metal at non-metal. So, during ionic bonding, yung metals yung naglulus ng electron para makapag-form siya ng positive ions. Then, yung non-metals naman yung nagigain ng nalus na electron para makabuo siya ng negative ions. So, usually, yung ionic compound ay hard, non-volatile, and high melting points. Then, yung covalent compound naman ay nabubuo sa pamamagitan ng covalent bonding. So, yung elements na involved dito ay dalawang non-metals. So, nangyayari yung covalent bonding kapag yung dalawang non-metals ay nag-share ng electrons. And usually, yung covalent compounds are gases and liquids with low boiling points. Yan. So, ceramics are inorganic and non-metallic materials. So, kapag inorganic, ibig sabihin, hindi siya carbon-based. And non-metallic, ibig sabihin, yung materials ay hindi magandang gamitin bilang conductor. Or hindi siya magandang gamiting material para makapag-conduct ka ng heat or electricity. Ceramics. The tradition of creating ceramics is something that started thousands of years ago with the invention of pottery, glass, and brick, and it's something which is continued today. New ceramic materials are being created in order to meet new challenge. Yung definition kasi ng ceramics ay napakalawak. Kumbaga, walang tiyak na definition para dito. At isa sa mga factors na naka-apekto dito ay yung kanyang aplikasyon sa buhay ng tao. Kasi nung mga nakalipas na panahon, nung wala pang mga gadgets and other equipments na ginagamit sa ating industry, yung ceramic, kapag binabanggit nila iyon, ang una nilang naiisip kaagad ay pottery. Kumbaga, ang purpose lang dati ng ceramic ay for pottery. At dahil sa mabilis na pag-unlad ng ating kaisipan at ating ekonomiya, lumawak yung pangangailangan natin sa pang-araw-araw. Kaya yung application ng ceramic ay lumawak rin. Kung dati for pottery lang siya, ngayon nagagamit na siya sa iba't ibang industry kagaya ng electrical at electronic industry. So isa yun sa mga factors. Then yung ikalawa, yung pagkakaiba-iba ng mga katangian ng mga ceramic materials. May ceramics kasi na inorganic or not carbon based at meron din namang carbon based tulad ng diamonds at graphite. Dahil dito yung mga material engineers sinati sa dalawang kategory yung ceramic at pinangalanan nila itong traditional ceramics at advanced ceramics. As mentioned previously, the properties of ceramics vary depending on design and application. However, many ceramics are known to have the following properties. Una, they are hard. Yung mga ceramics ay hindi madaling magbago yung size and shape. Kalawa, they are brittle, meaning they have a low resistance to impact. Ibig sabihin, prone sila sa fracture at pagkakaroon ng crack or bitak na nagiging cause ng kanilang pagkasira or pagkasira ng isang ceramic material. Katlo, they are refractory. Ibig sabihin, mataas yung resistant nila sa heat, pressure, and chemical attack. And last is, they do not conduct electricity. Kasi yung mga ceramics ay non-metallic. Ayan. Tulad nga ng nabanggit ko kanina, yung ceramics ay hinati ng mga material engineers sa dalawang kategorya. Ito ay ang traditional ceramics at advanced ceramics. So sa traditional ceramics, yung primary components na ginagamit ay clay, quartz or silica at feldspar. Habang sa advanced ceramics naman ay mostly ionic compound. Yung pinagkaiba ng dalawa ay yung kanilang pinagbalan kasi yung primary components ng traditional ceramics ay gawa ng kalikasan at habang yung advanced ceramics naman ay gawa ng tao base sa kanilang pangangailangan or paggagamitan. Yan. Ilan sa mga aplikasyon ng traditional ceramics ay makikita sa porcelain, tile, at bricks. Meron itong properties gaya ng brittle. Yung mga ganitong material ay prone to fracture. Next is yung hard properties. So, hindi sila madaling mabago or hindi madaling mabago yung kanilang size and shape every time na nakakaramdam sila ng stress or force. At last yung resistance to corrosion. Ayan, hindi sila kinakalawang. Yan, advanced ceramics. Also called as technical ceramics, high-tech ceramics, high-performance ceramics, engineering ceramics, and fine ceramics. So, yung term na engineering ceramics ay ginagamit sa United Kingdom, habang yung term naman na fine ceramics ay ginagamit sa Japan. Examples and its application. One of the examples of advanced ceramics ay yung alumina or aluminum oxide. Ito yung kombinasyon ng aluminum at oxygen. Ilan sa mga application nito ay makikita sa medical industry. Halimbawa, halimbawa nito yung bionic implant. Ilan sa mga properties ng aluminum oxide ay yung pagiging hard, o yung hindi madaling mabago yung size and shape. Then high compressive strength o yung hindi nila pagiging madaling or hindi sila madaling makompress. Next is yung high resistance to corrosion. Yan, hindi sila kinakalawang. And high strength. Yan, yung mga advanced ceramics mostly ay matitibay. Kaya maganda silang gamitin sa mga industry. Sila yung mostly na ginagamit ngayon sa industry because of their strength. Ceramic structures. Karaniwan sa mga ceramics ay binubuo ng dalawa o higit pang elements. Tinatawag na compound yung dalawang elements na pinagsama. For example, alumina or aluminum oxide is a combination of aluminum atoms and oxygen atoms. The two most common chemical bonds for ceramic materials are covalent and ionic. So, kapag covalent, yung dalawang elements na involved ay dalawang nonmetals. Habang kapag ionic bond naman ay ang dalawang elements na involved ay metal and nonmetal. Ceramic structures are little more complex than metallic structures. Dahil compound yung ceramic ay komplikado ng bahagya yung structure niya kaysa sa structure ng metal. Crystal structure is a unique arrangement of atoms in a crystal. So, atoms, tumutukoy ito sa smallest particle ng isang element. At yung particle na yun ay tumutukoy sa proton or positive charge, electron or negative charge, at neutron. Then, yung properties ng isang ceramic material ay nakadepende dun sa magiging structure niya. So, nag-iiba-iba yung properties ng ceramic base sa kanilang crystal structure. Ilan sa mga halimbawa ng crystal structure ay yung makikita natin sa ibaba. Affecting crystal structure. Una, the charge magnitude on each ion. Pangalawa, the radius of each type of ion. The charge magnitude on each ion. So, kailangan electrically neutral yung isang crystal. Ibig sabihin, yung bilang ng cation ay equal doon sa bilang ng anion para maging balance yung compound. Kinakailangan kasi na yung net charge ng structure ay 0. Halimbawa, meron tayo ditong dalawang elements. Ito ay ang calcium or Ca at fluorine or F. Yung calcium may dalawang positive charge or cations habang yung fluorine ay may isang negative charge or anion. So, para maging balance sila ay kinakailangan magdagdag ng isa pang fluorine para yung net charge nila ay mag-equal sa 0. Next, the radius of each type of ion. So, ito yung pangalawang characteristics na nakakaapekto sa crystal structure ng ceramic. Dito, dapat tandaan natin na yung size ng cation ay karaniwang maliit kesa sa size ng anion. And yung ratio of cations radii and anions radii is less than unity, meaning less than to 1. Stable and unstable configuration. So, masasabi nating stable yung compound kapag yung cation ay nakadikit sa mga anions na nakapaligid sa kanya, kagaya ng makikita nyo sa larawan. So, dito naman yung table. So, sa column 1, makikita nyo yung ratio ng cations radii at anions radii. So, less than unity yan or less than 1. Sa column 2 naman, makikita nyo yung coordination number. Then, sa column 3, makikita nyo yung coordination geometry. So, kapag yung coordination number ng compound ay 2, yung coordination geometry nila ay linear. Kapag yung coordination number naman ng compound ay 3, yung coordination geometry ng compound na yun ay triangular. Kapag yung coordination number naman ng compound ay 4, yung coordination geometry naman nila ay tetrahedral. Then, kapag yung coordination number nila ay 6, yung coordination geometry naman nila ay octahedral. Then, last, yung kapag coordination number ng compound ay 8, yung coordination geometry naman nila ay cubic. So, ayan lang yung mga dapat natin tandaan dito. Next, ito naman yung table para sa ionic radii for several cations and anions for a coordination number of 6. So, ayan, kung mapapansin nyo, yung unit ng ionic radius ay nanometer. So, napakaliit niyan. Common ceramic crystal structures. So, una, AX type crystal structures. Kalawa, A sub M, X sub P type crystal structures. At ikatlo, A sub M, B sub N, X sub P type crystal structures. So, sa AX type crystal structure ng ceramic, yung number of cations ay equal doon sa number ng anions. So, yung A, tumutukoy siya sa cation, habang yung X naman ay tumutukoy sa anion. So, ilan sa mga halimbawa ng AX crystal structure ay ang rock salt structure, cesium chloride structure, at zinc blende structure. So, yung rock salt structure ay binubuo ng sodium at chlorine. So, kung mapapansin nyo, equal yung number ng cations doon sa number ng anion. So, yung radii ng sodium ay equal to 0.102 nanometer. Habang yung radii naman ng chlorine ay equal to 0.181 nanometer. So, yung ratio nila ay equal to 0.564. Then, yung coordination number nila is 6. Kaya, yung coordination geometry nila ay octahedral. So, ayan yung itsura ng rock salt structure. So, yung rock salt structure ay maliit na bahagi lang ng rock salt. Next, cesium chloride structure. So, meron tayo ditong cesium at chlorine. So, yung ratio nila ay equal to 0.939. Kaya, yung coordination number nila is 8. At yung coordination geometry nila ay cubic. So, ayan yung itsura ng cesium chloride structure. Next. So, yung cesium chloride structure ay maliit na bahagi lang ng cesium chloride. Ayan. So, zinc blende structure. So, yung zinc blende structure ay binubuo ng zinc at sulfur. Yung coordination number nila is 4. Kaya, yung coordination geometry nila ay tetrahedral. So, ayan yung itsura ng zinc blende structure. Yung zinc blende structure ay maliit na bahagi lang ng zinc blende. Next, A sub M, X sub P type crystal structure. So, dito naman, hindi na equal yung number ng cations dun sa number ng anions. So, example nito yung calcium at chlorine. Yung calcium, meron siyang dalawang charge or dalawang positive charge, habang yung chlorine naman meron siyang isang negative charge. Yung ratio nila ay equal to 0.752. Kaya yung coordination number nila is 8. At yung coordination geometry nila ay cubic. So, ito yung itsura ng fluorite crystal structure kapag pinagsama yung calcium at chlorine. Next, so dito na tayo sa last. A sub M, B sub N, X sub P type crystal structures ng ceramic. So, dito meron tayong dalawang magkaibang element na may positive charge, then meron tayong isang element na negative charge. So, isang example niyan, kapag pinagsama-sama yung tatlong yan ay yung barium titanate. So, yung coordination number nila kapag pinagsama-sama mo sila is 6. At yung coordination geometry nila ay octahedral. So, ayan yung itsura ng structure nila. Tinatawag na perovskite crystal structure. Silicate ceramics. Silicates are materials composed primarily of silicon and oxygen, the two most abundant elements in Earth's crust. Ilan sa mga halimbawa ng silicates ay yung soils, rocks, clays, and sand. So, naturally, occurs yan. So, ibig sabihin gawa ng kalikasan. So, ito yung figure 1 na nagpapakita ng coordination geometry ng silicate. Silicate ceramics include the following. Una, the crystalline silica. Kalawa, layered silicates. At ikatlo, yung non-crystalline silica glasses. Crystalline silica structure. Chemically, the most simple silicate material is silicon dioxide or silica. It is a three-dimensional network that is generated when the corner oxygen atoms in each tetrahedron are shared by adjacent tetrahedra. Thus, the material is electrically neutral and all atoms have stable electronic structures. So, kung matatandaan nyo kanina, yung characteristics affecting the crystal structures. So, dito, kinakailangan electrically neutral and stable yung structure. So, para maging stable siya, kailangan yung net charge niya ay equal to 0. So, makikita nyo sa figure 2, ito yung arrangement of silicon and oxygen atoms in unit cell of cristobalite. So, yung cristobalite, ayan yung tawag sa structure ng crystalline silica. Next, layered silicates. A two-dimensional sheet or layered structure can also be produced by the sharing of 3 oxygen ions in each of the tetrahedra as shown below. Ayan, so yan yung itsura ng layered silicates. Non-crystalline silica glasses. So, ayan naman yung itsura niya. Silicate ceramics include the following. Una, the crystalline silica. Kalawa, layered silicates. At ikatlo, yung non-crystalline silica glasses. Crystalline silica structure. Chemically, the most simple silicate material is silicon dioxide or silica. It is a three-dimensional network that is generated when the corner oxygen atoms in each tetrahedron are shared by adjacent tetrahedra. Thus, the material is electrically neutral and all atoms have stable electronic structures. So, kung matatandaan nyo kanina, yung characteristics affecting the crystal structures. So, dito, kinakailangan electrically neutral and stable yung structure. So, para maging stable siya, kailangan yung net charge niya ay equal to 0. So, kung makikita nyo sa figure 2, ito yung arrangement of silicon and oxygen atoms in unit cell of cristobalite. So, yung cristobalite, ayan yung tawag sa structure ng crystalline silica. Next, layered silicates. A two-dimensional sheet or layered structure can also be produced by the sharing of 3 oxygen ions in each of the tetrahedra as shown below. Ayan, so yan yung itsura ng layered silicates. Non-crystalline silica glasses. So, ayan naman yung itsura niya. Material of importance. Carbon. Carbon is the most important element to living things because it can form many different kinds of bonds and form essential compounds. Ayan. So, yung carbon, madali siyang i-combine sa iba't ibang elements. At yung compounds na nabubuo ay napakahalaga sa iba't ibang field sa industry. Carbon is used for fuel in the form of coal, methane gas, and crude oil. So, yung carbon, napaka-importante rin niya para sa mga fuel, para makapag-create tayo ng heat and power. And ginagamit din yung carbon para makapag-create tayo ng plastics and alloys. So, alloys kagaya ng steel. So, yung steel is a combination of carbon and iron. So, yung carbon, ginagamit din siya sa paggawa ng mga ink ng printers and painting. So, ayan. Life on Earth is generally referred to as carbon-based life. So, yung buhay nga natin nakadepende sa carbon. Kumbaga, kung walang carbon, paano na lang kaya yung field ng electrical, paano na lang kaya yung field ng electronics, paano na lang kaya yung field ng automotive. So, kung walang carbon, paano aandar yung ating mga sasakyan, paano tayo makapag-generate ng electricity. Ayan. Next, carbon is found on Earth in the form of 3 different allotropes including amorphous, graphite, and diamond. Yan, kagaya ng sinabi ko kanina, yung ceramics ay inorganic pero may mga ceramics kasi na kino-considered na carbon gaya ng graphite and diamond. So, diamond. Diamond is transparent in color. Diamonds are used to make fine jewelry and considered as the most valuable of all the gemstones. Diamonds are also used for their hardness in cutting tools and precision instruments. So, ito yung itsura ng diamond cubic crystal structure. Next is yung graphite. Graphite is one of the softest materials and yung kulay niya is black-gray. Maganda ring electrical conductor yung graphite. So, maganda siyang gamitin bilang electrical conductor. So, karaniwang ginagamit yung graphite para makagawa tayo ng batteries, brakes, and lubricants. Ginagamit din to sa mga lapis natin. Ayan, yung black part ng lapis natin, ginagamit din yan. So, ito yung graphite structure o yung itsura ng graphite structure. Last material of important is yung carbon nanotube. Carbon nanotubes are tubes made of carbon with diameters typically measured in nanometers. So, napakaliit nito. Kaya, importante sa buhay natin ngayon. Kasi, kung wala yan, wala tayong magagamit ngayon na mga laptop, cellphone. Bukod dyan, malaki rin yung naitulong nito sa automotive, aeronautic, and space industry. Then, bukod dyan, maganda rin yung naitulong nito sa industrial engineering. Kagaya nagagamit siya sa paggawa ng mga rotor blades ng wind turbine. So, para makapag-harness tayo ng or makapag-harvest tayo ng energy na nagmumula sa wind tapos i-convert natin into electrical. So, carbon nanotubes yung ginagamit na material para makagawa tayo ng rotor blades. Bukod dyan, magaan din ito at bukod sa magaan ay matibay din. Kaya best talaga siyang gamitin sa iba't ibang field sa industry. Imperfections in ceramic. So, dito nagaganap yung atomic point defect na kung saan yung atom ay nawawala or nasa maling placement. Ilan sa mga halimbawa nito ay yung anion vacancy or yung pagkawala ng anion or negative charge dun sa particular place. Gaya na nakikita nyo sa picture. Then, meron din tayo dito cation vacancy. Ibig sabihin, nawawala naman dito yung cation or positive charge. At last is yung cation interstitial. Dito nangyayari naman yung maling placement ng cation or positive charge tulad nung nakikita nyo sa picture. So, ayan. So, kagaya nung sinabi ko kanina sa previous slide, para maging stable yung isang ceramic structure ay kinakailangan yung cation ay matatouch yung nakapalibot sa kanya na anion. So dito sa figure na ito, nakaka-apekto yung imperfection in ceramic sa stability ng particular ceramic material. Next. So, dahil sa imperfections in ceramic, nagkaroon ng dalawang types ng point defect. At tinawag itong Frenkel defect at Schottky defect. So, sa Schottky defect, dyan na nangyayari yung nababakante yung pwesto ng cation at pwesto ng anion. So, sabay na nababakante yung dalawang pwesto. Habang sa Frenkel defect naman, dito naman nangyayari yung pagmamigrate nung cation papunta sa ibang place. Ayan, kagaya ng nakikita nyo sa picture. So, nasa maling placement yung cation. So, nakaka-apekto itong mga point of defects na to sa stability ng ceramic material. Diffusion in ionic materials. Diffusion refers to movement or motion. Ionic materials. An ionic compound is a chemical compound comprising ions held together by electrostatic force. Term by ionic bonding. So, alam natin kapag ionic bonding, yung dalawang elements na involved is metal and non-metal. The compound is neutral overall, but consists of positively charged ions called cations and negatively charged or anions. Characteristics of ionic bonding. Ionic compounds are usually hard, rigid, and brittle. The results of being held in specific position. Ayan. So, kung makikita nyo sa picture, yung particular ionic compound or ceramic material is naka-experience ng force. So, once na maka-experience siya ng external force, nagkakaroon ng repulsion or nagre-repel yung mga charges na bumubuo sa kanya. Kagaya nung nakikita nyo sa picture. So, once na mag-repel yan, magkakaroon na yan ng bitak or crack na nagiging cause na pagkasira ng particular ionic compound or ceramic material. Because of this, nade-determine natin yung properties ng particular material. Especially kung nagkakaroon yan ng bitak bago yan masira, ibig sabihin ceramic material yan. And isa pa sa mga properties ng ceramic material is yung pagiging hard. Ibig sabihin, di na nagbabago yung size and shape nila bago sila masira. Then, rigid. Rigid yung hindi sila madaling mabaluktot or not flexible. So, ayan. Ayan yung mga usual properties ng ionic compounds. Then, diffusion in ionic materials. Diffusion in these materials usually occurs by a vacancy mechanism in order to maintain charge neutrality in ionic material. So, isa nga sa nakakontribute ng charge neutrality sa ionic materials is yung tinatawag na interstitial impurity atom. Then, meron pang isa, tinatawag din siyang substitutional impurity atoms or ions.
Ceramic phase diagram. Figure 9 is the aluminum oxide, chromium oxide phase diagram. Isa ito sa mga simpleng ceramic phase diagram. It consists of single liquid phase region, yung sa bandang taas. Ito. Sa bandang baba naman ang single solid phase region. Ito siya. These two regions, the liquid phase and solid phase regions, nasi-separate ng two phase solid liquid region. Ito yung blade shape, yung kulay red. Siya yung naghahati sa dalawang regions, yung liquid phase and solid phase. Ito yung two-phase solid liquid region. Siya yung naghahati dun sa liquid and solid phase regions. Kung titingnan natin sa left part ng diagram, dito yung temperature in degrees Celsius. Then, dito naman sa right side, yung temperature in Fahrenheit. Itong blade shape na ito ay mula 2045 positive, negative 5 degrees Celsius. Then, hanggang 2,275 positive, negative 25 degrees Celsius. If yun yung titignan natin sa temperature in Celsius. Sa taas nakalagay ang composition ng molecule percent and composition ng weight percent ng chromium oxide. Next diagram is the magnesium oxide, aluminum oxide diagram. On the right side is the temperature in Fahrenheit. And on the left side is the temperature in Celsius. Meron itong isang compound na tinatawag na spinel. Ang spinel ay ang magnesium aluminum, member of the larger spinel group of minerals. It has a formula of magnesium aluminate in the cubic crystal system. Ang spinel na sinasabi ay ang part na ito. Ito na may formula ng aluminate ay ano pala, yung magnesium aluminate. Ito yung spinel na sinasabi na may formula ng magnesium aluminate. Kahit na ang spinel ay isang natatanging compound, it represented on the phase diagram as a single phase field. It has a compositions of 50% molecules in aluminum oxide or 50% molecules in magnesium oxide. Dito siya tatapat. Ito yung 50% ng molecules of aluminum oxide and magnesium oxide. And tatapat siya sa composition weight percent mula sa aluminum oxide is 28 weight percent. Then if mula naman sa magnesium oxide, it has 72% weight. Dito. Mula sa magnesium oxide, ito yung 78% weight niya. Then kapag sa aluminum oxide, ito naman ay 28% weight. Bukod sa spinel, there is limited solubility of aluminum oxide in magnesium oxide. Below 1,400 degrees Celsius sa left side makikita. Ito yung limited solubility of aluminum oxide in magnesium oxide. Ito yung 1,400 degrees Celsius, which is due primarily to the differences in charge and radii of the magnesium and aluminum ions. In some reasons, magnesium oxide is virtually insoluble in aluminum oxide. Also, two eutectics are found on the other side of the spinel phase field. Ito siya yung isang eutectic na makikita sa diagram. Ito. Katabi ng spinel. Then yung isa naman makikita sa about 2,100 degrees Celsius. Ito. 2,100 degrees Celsius. Ito siya. Yung isang eutectic na sinasabi. Next diagram is the portion of the zirconia calcia phase diagram. We can observe from the diagram that zirconium oxide phases having three different crystal structures exist in this system: the tetragonal, monoclinic, and cubic. Tetragonal, monoclinic, and cubic. Pure zirconium oxide experiences a tetragonal to monoclinic phase transformation at about 1150 degrees Celsius. 1150 degrees Celsius. Ito siya. Ito yung nagpapakita ng tetragonal to monoclinic phase transformation. Ito. A relatively large volume change accompanies this transformation, resulting in the formation of cracks that render a ceramic ware useless. This problem is overcome by stabilizing the adding between 3 and 7% weight of calcium oxide. Ito. Ito yung sinasabi na stabilize, na tinatawag na zirconia. Ito yung nakatapat sa 1000 degrees Celsius. Sa taas naman nito ay makikita ang cubic and tetragonal phases. Ito. Upon cooling to room temperature under normal cooling conditions, the monoclinic at itong formula na to ay hindi nag-form. Consequently, the cubic and tetragonal phases are retained and crack formation is circumvented. May mga liquid, cubic liquid, liquid and calcium zirconium oxide, cubic zirconium oxide, calcium zirconium oxide. Next diagram is the silica alumina phase diagram. Commercially, the silica alumina system is an important one because the principal constituents of many ceramic refractories are these two materials. Silica and alumina are not mutually soluble in one another, which is evidenced by the absence of terminal solid solutions at both extremes of the phase diagram. Also, it may be noted that the intermediate compound mullite exists, which is represented as a narrow phase filled in the diagram at 1890 degrees Celsius or 3435 degrees in Fahrenheit. Ito siya. Ito yung mullite compound. Also, a single eutectic exists at 1587 degrees Celsius. Ito. And has a 7.7% weight of aluminum oxide. Ito yung 7.7. Ito. 7.7 weight. 7.7 weight of aluminum oxide. Ito yung isang eutectic na nag-exist dito sa diagram na to. Mechanical properties. Between 3,000 and 400 years ago, metals came into widespread use because of their toughness that is derived from their ductility. For most of that history, ceramic materials were somewhat limited in applicability because of their brittle nature. Bago ang panahon ng tanso, ang mga kagamitan ng tao ay at imbakan nila ay karaniwang gawa sa bato. Between 3,000 and 400 years ago, ang paggamit ng metal ay laganap dahil sa matigas at matibay ito. Most of that history, the use of ceramic materials is somewhat limited because of its brittleness. Bagaman maraming mga bagong pinaghalo at iba pang mga multi-phase na ceramics na binuo at mas may pakinabang, yung mga brittle pa rin ang ginagamit sa kasalukuyan. The brittle fracture process consists of the formation and propagation of cracks through the cross-section of material in direction perpendicular to the applied load. Crack growth in crystalline ceramics may be either transgranular, example, through the grains, or intergranular along grain boundaries. For transgranular fracture, cracks propagate along specific crystallographic or cleavage planes of high atomic density. Ang intergranular fracture ay nangyayari kapag ang crack ay kumalat hanggang sa dulo o hangganan ng isang material, lalo na kapag ang hangganan ng material na ito ay humina na. Ang transgranular fracture naman ay nangyayari kapag lumalaki ang lamat sa bawat piraso ng material. The measured fracture strengths of most ceramic materials are substantially lower than predicted by theory from interatomic bonding forces. This may be explained by very small and omnipresent flaws in the material that serve as stress racers, points at which the magnitude of an applied tensile stress is amplified, and no mechanism such as plastic deformation exists to slow down or divert such cracks. Ang mga stress racers na ito ay tinatawag na interior cracks or micro cracks, internal pores, inclusions, and grain corners na imposible nang matanggal at hindi na makontrol, hindi na kayang kontrolin. For example, even moisture and contaminants in the atmosphere can introduce surf cracks in freshly drawn glass fiber that can affect its strength. Ang stress concentration sa dulo ng isang material ay pwedeng magdulot ng crack at lumala pa at masira na ng tuluyan ng isang material. The measure of a ceramic material's ability to resist fracture when a crack is present is specified in terms of fracture toughness. The plane strain fracture toughness is defined according to the expression. This expression, where y is a dimensionless parameter of or function that defines depends on the both specimen and crack geometries. Stress is the applied stress. A is the length of a surface crack or half of the length of an internal crack. Next. Fractography of ceramics. It is sometimes necessary to acquire information regarding the cause of a ceramic fracture so that measures may be taken to reduce the likelihood of future incidents. As a failure analysis normally focuses on determination of the location, type, and source of the crack initiating flow. A fractographic study is normally a part of such an analysis, which involves examining the path of crack propagation as well as microscopic features of the fracture surface. Ang fractography ay isang teknik na ginagamit at ginagawa upang maintindihan kung ano ba ang mga causes ng failures o dahilan ng pagkasira ng isang bagay o material. Also, to verify din ang mga theoretical failure predictions sa totoong buhay. For brittle ceramic materials, schematic representations of cracks origins and configuration that results from this: A. Impact or point loading, next bending, then torsion, then internal pressure. Figure 13. This is the schematic diagram that shows typical features observed on the fracture surface of a brittle ceramic. There is the source of the failure here. The mean region is a faint annular region. Beyond the mean is the hackle, which has an even rougher texture. Yan, the hackle. And the smooth mirror region. Ito. Stress-strain behavior. Flexurial strength. A 3-point loading scheme for measuring the stress-strain behavior and flexurial strength of brittle ceramics, including expressions for computing stress for rectangular and circular cross-sections. Looking at the figure, at the point of loading, the F here, the top surface of the specimen is placed in a state of compression, whereas the bottom surface is in tension. The stress is computed from the specimen thickness, the bending moment, and the moment of inertia of the cross-sections. The parameters for rectangular cross-section are here. Itong mga ito. Ayan yung mga parameters for rectangular cross-sections. Sa circular cross-section naman, ay itong mga to, where M is the maximum bending moment, C is distance from center of specimen to outer fibers, I is moment of inertia of cross-section, and F is the applied load. The stress is fracture using this flexure test is known as the flexural strength, modulus of fracture strength, or bend strength, an important mechanical parameter for brittle ceramics. and circular cross-section. The flexural strength is given by these formulas. This is for rectangular cross-section and this formula is for circular cross-section, where F is the load of fracture, L is the distance between support points, and R is the specimen radius. Elastic behavior. Figure 14. Typical stress-strain behavior to fracture for aluminum oxide and glass. This figure compares the stress-strain behavior to fracture for aluminum oxide and glass. The slope in the elastic region is the modulus of elasticity. Here, itong slope. The range of this modulus of elasticity for ceramic materials is between 70 and 500 gigapascal. It being slightly higher than for metals. Also, note that the material will not experience plastic deformation before the fracture. Mechanisms of plastic deformation. Under mechanism of plastic deformation is crystalline ceramics. For crystalline ceramics, plastic deformation occurs as with metals by the motion of dislocations. One reason for the hardness and brittleness of these materials is the difficulty of slip or dislocation motion. For crystalline ceramic materials for which the bonding is predominantly ionic, there are very few slip systems, crystallographic planes, and directions within those planes along which dislocations may move. This is a consequence of the electrically charged nature of the ions. For slip in some directions, ions of like charge are brought into close proximity to one another. Because of electrostatic repulsion, this mode of slip is very restricted to the extent that plastic deformation in ceramics is rarely measurable to room temperature. Next. However, for ceramics in which the bonding is highly covalent, slip is also difficult, and they are brittle for the following reasons. First one is the covalent bonds are relatively strong. There are also limited numbers of slip systems, and dislocation structures are complex. Next, non-crystalline ceramics. Plastic deformation does not occur by dislocation motion for non-crystalline ceramics because there is no regular atomic structure. Rather, these materials deform by viscous flow, the same manner in which liquids deform. The rate of their deformation is proportional to the applied stress. In response to an applied shear stress, atoms or ions slide past one another by the breaking and reforming of interatomic bonds. However, there is no prescribed manner or direction in which this occurs as with dislocations. The characteristic property for viscous flow, viscosity, is a measure of a non-crystalline material's resistance to deformation. For viscous flow in a liquid that originates from shear stresses imposed by two flat and parallel plates. The viscosity is the ratio of the applied shear stress and the change in velocity with distance in a direction perpendicular to and away from the plates, or this expression, which viscosity is equal to shear stress over dv, or the velocity over dy, or the distance, or f over a divide dv over dy. The units for viscosity are poise and Pascal seconds. 1 poise is equal to 1 dyne second per centimeter squared centimeter, and 1 Pascal second is equal to 1 Newton second per squared meter. Conversion from one system of units to the other is according to 10 poise is equal to 1 Pascal second. Figure 15, representation of the viscous flow of a liquid or fluid glass in response to an applied shear force. F is the viscous flow here in the figure 15, and A is the liquid or fluid glass. Then V and Y are the velocity and distance in a direction. That's all. Thank you for listening.